Hello and welcome to a new series of videos I'm doing here on movingelectrons.com. This is new as of March 2017, so if you're watching this anytime in the future, it won't probably be as new. What are these series of videos? Well, I'm going to be taking topics that are going to be tested on the Power PE exam. For those of you who are unfamiliar, the Power PE exam is a mandatory exam for electrical engineers in the United States that want to get their professional engineering license. So, if you're not in the United States or are not interested in writing this exam, but are an electrical engineer or an electrical engineering student who are interested in any of these topics, I'll still encourage you to watch these videos because they'll still provide value to you. These are relevant for any power systems engineer anywhere in the world. And the way we're going to go about doing these videos is I'm going to take a problem that might potentially appear in one of these exams, and we're going to then solve that problem. But not only are we going to solve it, we're going to also look at the concepts behind them, so we better understand why we are doing the steps that we are following to solve the problem. Today's topic is power factor correction, and without taking any more of your time, let's look at the problem and let's try to understand this concept of power factor correction a little bit better. So what we've been told is that there's a three-phase 460 volt 40 horsepower induction motor which draws 45 amps at 0.78 lagging power factor from a 480 volt source. And we've been asked what is the reactive power required to correct the power factor to zero point 0.9 lagging. So the question is to find the reactive power. Let us. So what I like to do in these kind of problems before we dive in is to kind of get a visual by drawing like a single line diagram for that, right? So let's just draw a single line here. So let's say this is a bus, 480 volt bus, and then that's the feeder for this three-phase motor. This is our 40 horsepower motor. The system values we've been given is it's a 480 volt system. It is currently drawing 45 amps, and the power factor existing is 0.78 lag. Now what you see here is the nameplate information for the motors given 460 volts and 40 horsepower. This is a NEMA standard that for any 480 volt system, the motor manufacturers state that they can operate the motor at 460 volts. This is just to account for any voltage drop that might be there in the system. But one thing you have to be careful about if you're doing any calculations, you should use 480 volts because that's the system voltage, and that's what we'll be using as well. And you'll see that, and I'll point that out once again when we get into the solution of the problem. One of the other things to keep in mind is whenever we have a problem for a power factor correction, one of our starting points is the power triangle. If you're unfamiliar with it, this is a right angle triangle where the x-axis is the real power P, the y-axis is the reactive power Q, and the resultant here is the apparent power S. Now note, this is the apparent power S. This is the magnitude of our complex power. So if you remember complex power, that's a vector, is given by VI conjugate. Do not confuse this with this. This is the magnitude of this. So S here is nothing but VI, just the magnitudes. Then we have the power factor angle here, theta. Now if you see this, if this is VI, this is theta. If we go to our trigonometry, what does that say? What is this side going to be? This is going to be S times cos theta, or VI cos theta. because from trigonometry we know that if we say this is triangle AB and C, cos of theta is AB over AC. AC we see here, this side AC is nothing but the apparent power S, which is given by VI. So you have VI cos theta, and similarly you have Q as being equal to VI sine theta. This is the equation, if you remember, for the single phase real power. That's VI cos theta and VI sine theta for the reactive power. If we have a three-phase system like we do here, we introduce the term root 3, and we introduce the term root 3, and we introduce the term root 3 here. Also, what we need to know from here, we can define power factor. The definition of power factor is it's the cosine of the angle between the real power and the apparent power. So, what is power factor? It is the cosine of the angle between these two. So it is cos theta. And what is cos theta? We just said AB over AC. What is the side AB? It is the real power P. And what is the side AC? It's the apparent power S. So power factor can be defined as cos theta, or it can be defined as a ratio between the real power and the apparent power. It's okay, what else do we need to know? Now, since we have this definition in place, let's go back to our problem. So we've been given two power factors. One's an existing power factor 0.78 lagging, and one is a new power factor 0.90 lagging, which is what we want to get to. If you see the relation cos theta is equal to power factor, let us now investigate that a little bit more. What is cos of 0 degrees? That's 1. What is cos of 90 degrees? That's 0. And any angle in between takes a value between 1 and 0. So what we find out from here is as the angle increases, this value decreases. So going back to our equation here, cos theta is equal to power factor. As this angle theta would increase, our power factor would decrease. And a low power factor is undesirable. And that's why I'll get into that a little bit later as well. I'll show you why a low power factor is undesirable. And that's what we're really doing here. We are improving our power factor, right? From 0.78 to 0.9. So at a lower power factor, our angle would be more. So if we were to draw a power triangle for our first system where the power factor is 0.78 lagging, if this is going to be, let me draw that. Let us just say that this is the power triangle for power factor equal to 0.78 lag, right? And then this is our angle theta existing because this is power factor which is existing. Now, what do you imagine would be if this, for our new power factor 0.90, this angle is going to be a lot smaller, right? Because our power factor is better. So our triangle is going to become something like this. This is the power triangle for power factor new, which is 0.90 lag. And this is our new theta, theta new. What's the key difference here? Now, what you have to remember is when you are changing the power factor, you don't want to change the real power, because the real power being absorbed by the motor is going to remain the same. The motor is still, you want the motor to continue doing the work that it's doing right now, right? So you want to give, it's still going to have the same mechanical output, therefore it's still going to draw the same real power. Real power is the power that's doing the work, correct? So what changes? The reactive power changes. So in this case, you have this reactive power, which is, let's say, Q existing. And in this case, when you have changed the power, you have improved your power factor, you have Q new. This Q new is a lot less than QE, but the real power is going to remain the same. So if we overlap these two, let us overlap these two power triangles. So this is the power triangle for the case where your power factor is 0.78, and then when your power triangle is for your power factor of 0.90, it's going to become a lot smaller, right? And let's see what the Q values are. So this, let me just draw a straighter line there. So this is Q existing, this is Q new, and this is the difference that is Q, let's call that's the Q that we have to add. And I'll show you why we have to add that. So what's the reactive power required? This is the reactive power that is required to change the power factor from which corresponds to theta existing to the one that is with theta new. That's the reactive power that needs to be added to the system. So what's happening right now? It's an induction motor, it's a lagging power factor. So we have Q existing being absorbed. Even Q new is 0.90 lagging. It's a lot less, but it's still being absorbed by the system. QA on the other hand, so this is your reactive power requirement for the motor is going to remain the same. What's going to happen is you're going to provide that reactive power locally, and that's why we introduce capacitors. But that's a topic we'll discuss later. So what's happening is QA is in this direction almost. So what we get from that is Q additional is going to be QE minus QN, but there's going to be a negative sign here because the direction of QA, it's going to be opposite, right? So this is how we're going to get the reactive power required, and you know it's going to be one of these two answers because it's going to be have a negative sign next to it. Okay, so now let's look at the steps for the solution. Before we even go there, let me just note down what are the formulas we're going to use. Formulas to be used. We have to find out the reactive power. So reactive power, we just said, is VI sine theta. It can also be expressed in terms of the real power P as P tan of theta, right? If you again go back to trigonometry, tan theta is going to be Q over P, therefore Q is P tan theta. What is theta going to be? It is cos inverse of our power factor. And what is real power P? We know that it's going to be root 3 VI of cos theta or power factor. So we'll first calculate P, then we'll calculate our theta, we will substitute in there and we will get Q. So let's look at our solution. Step 1 is we're going to calculate the power requirement for the motor. That's going to be root 3 times 480. Remember how I said we have to use the system voltage and not the nameplate voltage? So we have 480 times the current. The current is given to us as 45 times the power factor. So the power factor is 0.78. And that's going to give us a value of 29.18 kilovolts. Step 2, we're going to find out the theta. So they're going to be, so remember the real power is going to remain constant. So real power, so this is our PM. Theta, we're going to have two values, theta existing and theta new. So theta existing is going to be cos inverse of the existing power factor, which is 0.78. This should give us a value of 38.24 degrees. Theta new is going to be cos inverse of the new power factor, which is 0.90. This is going to be 25.84 degrees. Now, did you see these values? This is what's expected, right? We expected theta existing to be greater than theta new, and that's what we have here. Theta existing is greater than theta new, and that is what was expected. So that means we're going on the right track. Step 3, we're just going to find out tan theta existing and tan theta new. So tan of 38.24 is going to give us 0.80. Tan of 25.84 is going to give us 0.48. Our final step is we're going to use this formula right here. QA is going to be negative Q existing minus Q new, which is going to be minus of what is going to be Q existing. It's going to be PM times tan of theta existing minus PM tan of theta new. If you calculate this, you should get the answer to be negative 9.34 kVAR, and therefore if we go up here, our right answer is option C. It is negative 9.34 kVAR. I hope you understand why we have the negative, how we calculated this. So these are 4 steps. So when you're solving the problem, obviously you don't need to go through all the concepts as long as you know these 4 steps. That's it. It's pretty simple, pretty straightforward. Before I summarize these 4 steps for you, let's look at one interesting fact. So let's now go back to this equation. What did we say? We said the PM is going to remain the same. So your PM in this equation is going to remain constant, 29.18. Your voltage is going to be 480. Your power factor has changed though, 0.9. So what other value is going to change here? The current is going to change. This value is going to change because this remains constant. This remains constant. But if this has changed, then something else must change here to keep it 29.18, right? And that's the current. So let's look at what the current is going to be. So if we have 480, so we have root 3 times 480 times this new current times the new power factor 0.90 is still going to be equal to 29.18 kilovolts. If you plug that in, you're going to get your new current is going to be 39 amps. So you see what has happened is when we improved the power factor, the current requirement from the motor, from that circuit reduced. And that is why a good power factor is desirable. A better power factor leads to smaller currents, and smaller currents has a lot of advantages. You can size your equipment to be a lot smaller. Your conductor sizes are going to be smaller. Your I square R losses are going to be a lot smaller. Your equipment life is going to increase. Your kVA rating is going to be a lot smaller. And this is the reason why utilities, if you have a poor power factor, they penalize you because they have to design their system to match to meet your poor power factor requirements, your high reactive power requirements. And reactive power is not doing any real work. The real work's only been done by P, right? But just because your power factor is poor, your currents are higher, and the system is going to be designed such. That's the reason why we desire a lower power factor, and that's why this is a real world issue where you'd want your power factors to be better. If you have a low power factor, you'd want to improve your power factor. And this is the calculations we did today is what you'll do to find out how many kVARs you need to introduce. Once you have your kVARs, then you can find out how to size your capacitors that you'll introduce in the circuits to introduce those, to bring those kVARs to the system. So that's the problem today that we solved. Just to summarize the steps for our solution: step one, calculate real power P. Step 2, calculate power factor angle theta. Step 3, calculate tan of theta. And step 4, you calculate your Q that needs to be added, which is negative of Q existing minus Q new. And the formulas that we're going to be using are given here. So you have those 3 formulas, you have these 4 steps, and you have everything you need to solve a problem which asks you to find out the reactive power that is required. Just pay close attention to what the system voltage is, what the currents are. Make sure you see the power factor, it should be lagging. As long as you keep in mind these factors, you should be able to solve a problem like this with ease. I'll give you a sample problem just so you can practice this. Let's see. Let's say the nameplate is, again, it's a 460 volt, this time a 30 horsepower motor. The system is a 3-phase system, 480 volts. The current that's being drawn is, let's say, 32 amps, and the existing power factor is 0.75 lagging. You want the new power factor to be 0.92 lagging, and for this you have to find out your Q additional. So try the sample problem. It's absolutely similar to the one we solved, but once you solve it yourself, you'll get a better understanding. Leave your solutions in the comment section below, or if you have any problems, if you have any comments on this new set of videos that I'm doing, please, I'd love to hear from you. Leave your comments, or you can just contact me at nimish@movingelectrons.com. Do subscribe to the channel, as I'll be posting a lot more of these videos as we move forward. Thanks for watching. Thanks for your time. I really appreciate it. I hope the videos bring some value to you. And I look forward to meeting you in the next video. Take care. Bye now.